A wall of concrete that makes its own electricity and stores it, and keeps doing both for as long as the building stands. A team at Southeast University in China built exactly that and announced it in May 2025 as the world's first self-powering, energy-storing concrete. That's not a typo. The wall itself is the battery and the generator. Clips of this are all over your feed right now, calling it a magic Chinese battery brick. But two of the biggest things those clips tell you are just wrong. And the truth is stranger than the hype. The strange thing is, the core of it is completely real, buried under a pile of exaggeration. Concrete is the most used building material on the planet. By weight, it's the most manufactured stuff we make, tens of billions of tons of it every single year, more than anything on Earth except water. And for 5,000 years, it's done exactly one job. It holds things up. Walls, floors, bridges, roads, foundations. Dead weight that carries load and does nothing else. So the idea that the gray stuff sitting in every building around you could run electricity through itself sounds like science fiction. It isn't. It's a lab result, it's published, and the numbers are real. The problem is, what happens on the way from the lab to your phone screen? Here's the first thing the viral posts get wrong. They keep calling it a battery. It isn't a battery. It's a supercapacitor. And that distinction is the whole reason this technology is interesting in the first place. A battery stores energy in a slow chemical reaction. You charge it. The chemistry changes. You discharge it. The chemistry changes back. And every time you do that, the chemistry wears out a little. That's why your phone battery is worse after 2 years. A supercapacitor doesn't rely on chemistry at all. It stores charge physically, on the surface of its electrodes, the way static electricity clings to a balloon. Ions rush onto the surface when you charge it and rush off when you discharge it, and because nothing is reacting, almost nothing degrades. It charges in seconds instead of hours. It survives hundreds of thousands of cycles, and it barely wears down. The trade-off is that a supercapacitor holds far less energy than a battery of the same size. So when someone films a concrete block lighting an LED and captions it, "This brick could power your house," they've skipped the part that matters. It can't power your house, not yet, and maybe not ever in the way they mean. What it can do is store a small amount of charge, release it fast, and keep doing that for decades without dying. Hold on to that, because it changes what this is actually for. Now the second thing the clips get wrong, and this one's about who did it first. The battery brick going viral didn't come out of China. It came out of a lab in Missouri in 2020. A chemist named Julio Darcy at Washington University in St. Louis figured out that an ordinary red brick is secretly the perfect skeleton for a supercapacitor. Red bricks get their color from iron oxide, the same rust-colored mineral, and they're full of tiny pores like a sponge. Darcy's team pumped acid vapor and a special gas into those pores, and the reaction grew a network of conductive plastic fibers all through the brick. That conductive web turned the brick into an electrode. Pair 2 treated bricks with a gel in between, seal it, and you've got a supercapacitor you can literally build a wall out of. 3 of them wired together hit 3.6 volts, enough to run a green LED, and the thing kept working after 10,000 charge cycles. It even kept a light glowing while the whole sealed brick sat submerged in water. The one catch was cost, since treating a brick ran about 3 times the price of a plain one. So the brick that everyone's crediting to China was actually an American proof of concept from 5 years ago, and it had a ceiling. Those bricks were strong enough for a decorative wall, but not strong enough to hold up a building. And they stored charge without ever generating a watt of their own, which is exactly the gap the Chinese team went after. They didn't copy the brick. They asked a harder question. What if the load-bearing material itself, the concrete a building is actually made of, could store power and make its own? To see why that's such a leap, you have to understand how you turn something as dumb as cement into an electrode in the first place. Cement is a terrible conductor on its own. Electricity basically refuses to move through it. But cement, once it sets, is riddled with microscopic pores, a fractal maze of tiny channels left behind as the water reacts and the material hardens. And that pore structure turns out to be the whole trick. A team at MIT showed this cleanly a couple of years ago. They mixed cement and water with carbon black, which is essentially very fine soot. And as the cement cured, the carbon didn't just sit there. It threaded itself through all those pores, following the maze, and grew into a connected network of conductive wire running through the entire block. Suddenly, the concrete could carry charge. The pores hold the electrolyte, the carbon network holds the charge, and the block becomes one giant supercapacitor. The reason this works at all comes down to surface area, which is where supercapacitors live or die. A supercapacitor stores charge on the surface of its electrodes, so the more surface you can cram into a fixed volume, the more it holds. And cement's internal pore maze is enormous. Unfold all those microscopic channels inside a single block, and the hidden surface area runs into the square kilometer range. The carbon threads coat that entire buried landscape, and every square inch of it becomes a place to park charge. From the outside, it looks like a solid, dull gray block. Almost all the action is happening on surfaces you can't see. The MIT team ran the math on scaling that up, and the number is worth sitting with. A block of their carbon cement about 45 cubic meters, roughly a 3.5 meter cube, could store around 10 kilowatt hours. That's about a day of electricity for an average home. Picture that for a second. Not a battery in the basement. The basement. Pour the foundation of a house out of this material, wire it to the solar panels on the roof, and the foundation quietly banks the day's sunshine and hands it back at night. Same idea for a road. Bury a layer of it under the asphalt, and in theory, the road could wirelessly top up electric cars as they drive over it. That's the American side of this race, and it's real, and it's why the whole field suddenly matters. And China hasn't been sitting on the storing side either. Over the last 2 years, a wave of Chinese labs has been racing to turn cement into a supercapacitor, and the numbers keep climbing. One team building what they call cement-based structural supercapacitors, weaving carbon fibers and carbon nanotubes through ordinary Portland cement, hit a storage figure high enough to keep a red LED lit for more than 9 minutes off a single small block. And they're aiming it squarely at charging pavements, roads that carry their own power. Another group folded a zinc-based chemistry into aerated cement mortar to get storage and load-bearing strength out of the same pour. A third held the concrete's compressive strength up around 41 megapascals, genuinely structural grade, while still making it store charge. So the storing wall isn't one lucky paper. It's a whole field, and China is crowded into it. But storing power is only half of what the Southeast University team pulled off, and it's the smaller half. Because storing electricity still means you have to get that electricity from somewhere first. Their concrete generates its own. This is the part the hype clips fumble completely, because it's genuinely hard to believe. The material makes electricity out of a temperature difference. The effect they're using is called the Seebeck effect, and it's been known for 200 years. When one side of certain materials is hotter than the other, the heat pushes charge carriers from the hot side toward the cold side, and that imbalance creates a voltage. A temperature gap becomes electricity, with no moving parts, no fuel, nothing spinning. The catch has always been that ordinary building materials are terrible at it. The voltage you get out is tiny. So the Southeast University team, led by Miao Changwen, an academician of the Chinese Academy of Engineering, spent their effort engineering the cement itself to be good at it. They built 2 versions, a P-type and an N-type, the 2 halves you need to make a working thermoelectric circuit by mixing special additives into the cement matrix. And the performance jump is the headline. Their thermoelectric cement hit a Seebeck value around 10 times higher than earlier cement-based materials. In plain terms, for the same difference in temperature, It produces roughly 10 times more voltage than anyone had gotten out of a cement before. Now think about where temperature differences already exist, for free, everywhere. The sunny side of a building versus the shaded side, the warm interior versus the cold exterior on a winter night, a road baking in the afternoon sun versus the cool ground beneath it, waste heat pouring off an air conditioner. All of that is a temperature gap the wall could be quietly turning into trickle current, all day, forever, for zero fuel. This isn't free energy in the physics teacher sense, to be clear. The heat was already flowing from the warm side to the cold side and mostly leaking away into the air. The wall just takes a small cut as it passes through, the way a toll booth takes a small cut from traffic already using the road. It's a trickle. But a trickle running on every outside wall of every building, all day and all night, adds up to something a single dramatic number never shows. So now you have a material that generates a little electricity from the heat moving through it. The obvious next question is where that electricity goes, and this is where the two halves click together. The same team also built the storage side to match, a self-charging cement supercapacitor with what they describe as a sandwich structure. Cement electrodes on the outside, a cement-based electrolyte in the middle, and the clever piece is that middle layer. That middle layer. The researcher who described the storage design, Joe Yang, explained that they gave the electrolyte an ordered, layered internal structure, almost like the veins of a leaf, which is why the whole thing gets called bio-inspired. That structure lets ions move through it fast while blocking electrons from taking a shortcut. Blocking that shortcut is the entire game in a supercapacitor, because a shortcut is a leak, and a leak is a battery that drains itself overnight. By tuning that microstructure, they push the ionic conductivity of the cement up by 6 orders of magnitude compared to ordinary cement. 6 orders of magnitude is 1,000,000 times. And they did it without giving up the strength that makes cement worth using, which is the trap every attempt like this falls into. Usually you make concrete better at electricity by making it worse at being concrete, softer, weaker, useless for holding anything up. They avoided that trade. The material stayed strong and got conductive. Put the two inventions next to each other, and you get the word that separates this from the American brick: self-charging. The thermoelectric cement sips voltage out of the heat moving through the wall, and the storage cement sitting right beside it catches that trickle and banks it around the clock with no solar panel, no wire from the utility, no input at all beyond the temperature gap the building already has. A wall that tops itself up on its own, slowly and silently, off nothing but the fact that one side of it is warmer than the other. That's the loop the hype clips never actually explain, and it's the part that took real work to close. Then there's the number that actually made me stop reading and reread it. After 20,000 charge and discharge cycles, their supercapacitor still held 95% of the capacity it started with. 95% after 20,000 cycles. If this is the kind of engineering breakdown you want more of, take a second to subscribe, because this channel digs into exactly these Chinese tech stories that the big outlets flatten into 10-second clips. To put that next to something familiar, a lithium battery in a phone or a car is usually considered worn out somewhere around 1,000 to 2,000 cycles. This cement shrugged off 20,000 and barely noticed. The team's own framing was blunt about what that means. A storage material this durable could last as long as the building it's poured into. You'd never replace it because it would outlive everything around it. That's the full picture the viral clips are butchering. Not a battery brick from China. A Chinese research team taking the load-bearing material buildings are already made of and giving it 2 new jobs at once, generating power from the heat passing through it and storing that power for decades without wearing out. Generate and store in the same gray block, rated to outlast the structure. Put that way, it almost sounds too good to be true, and parts of it, right now, kind of are. Because here's the honest part, the breathless videos will never tell you, and it matters. Right now, today, this is small. We're not talking about wiring your kitchen off a wall. The voltages these lab samples produce are modest. The amount of energy a block this size stores is a sliver of what a real battery holds. And the impressive demos are things like keeping an LED lit or running a small fan. The thermoelectric side only works while there's an actual temperature difference to feed on. And when the sun sets and the inside and outside even out, the generation drops toward nothing. This is a laboratory breakthrough, not a product you can order. Anybody selling you a Chinese wall that powers your whole home is selling you a fantasy that's years away, if it arrives at all. And there's a hard ceiling under all of it. The amount of energy you can pack into a supercapacitor is still only a small fraction of what the same volume of lithium battery holds. That gap is real. It comes straight out of physics, and it's exactly why nobody serious in this field claims the material replaces the battery in your car or the pack on your wall. What it changes is smaller and sneakier. It's the assumption that the concrete has to just sit there doing nothing. So why does any of it matter if a single block barely lights a bulb? Because you're thinking about one block, and the entire point is that you'd never use one block. You'd use the building. Every wall, every floor slab, every stretch of foundation, every column, all of it storing and skimming at once. One block is a rounding error. A city block is a power station nobody had to build anywhere, because it's the same concrete that was going up regardless. Concrete isn't a niche material you install in one corner. It's the skeleton of civilization. It's already in every wall, every floor, every foundation, every bridge, every mile of road, by the billions of tons. The energy any single square meter stores is tiny, but the surface area is effectively unlimited, because it's the surface of everything humans build. Storage that is the structure costs almost nothing extra to add, because the structure was going to exist anyway. There's no separate battery to buy, no rare metals to mine, no flammable chemistry to catch fire, and nothing that degrades and needs replacing on a 10-year clock. That's the actual prize, the concrete a building needs anyway, pulling a second shift for almost nothing extra. There's a bonus buried in that too. Cement is one of the largest single sources of carbon emissions on the planet, a material we can't stop making and can't seem to clean up. If the concrete we were always going to pour can also shave a building's energy draw, banking its own solar, running its own sensors, trimming what it pulls off the grid, then the dirtiest material we make starts paying back a sliver of its own debt. That's a reason to care that no 10-second clip is ever going to hand you. And this is where it stops being a lab curiosity and starts being a strategy. Because China isn't only running these experiments in a university, it's already deploying the grown-up version of the same idea at national scale. In late 2025, a project in Gansu province connected to the grid that pairs a giant bank of lithium batteries with a 25-megawatt array of supercapacitors, a combined system rated at 500 megawatts and a full 1,000 megawatt-hours of storage. Another site in Shanxi brought online what's been called the world's largest supercapacitor installation, a 58-megawatt block of them working alongside conventional batteries. The reason a country would build supercapacitor storage that big is the exact same reason the cement version is interesting. Supercapacitors respond in milliseconds, and they almost never wear out, so they catch the sudden swings that wind and solar throw at a grid, the gusts and cloud shadows that batteries are too slow and too fragile to absorb cleanly. And they do it for decades without being swapped out, which quietly changes the math, because you buy this kind of storage roughly once instead of rebuying it every few years. China added more new wind and solar last year than any country ever has in a single year, which means the swing problem there is bigger than anywhere on Earth, and the appetite for storage that's fast, cheap, and effectively immortal is bigger to match. Look at those two things side by side and the pattern is obvious. On one end, grid-scale supercapacitor farms stabilizing entire provinces today. On the other, research turning the concrete of individual buildings into tiny distributed versions of the same thing tomorrow. Both are chasing the same thing: storage that's cheap, lasts for decades, and can be spread across everything a country builds. Push that far enough, and the grid stops being a separate thing you plug into. The cities themselves become the grid. There's a strategic layer under the chemistry too. Whoever turns this into ordinary construction gets something bigger than a cheaper battery. They get buildings that lean less on the grid, cities that can ride out the swings of renewable power on their own mass, and an energy system that doesn't hang on mining. A long list of metals somebody else controls. For a country pouring more concrete and switching on more solar than anyone in history, that kind of independence is a big part of why the whole effort makes sense. And China isn't alone in seeing it, which is what makes this a race rather than a victory lap. The American brick started this. The MIT Foundation that stores a day of power is chasing the same future from the other direction. The science is genuinely open, and the lead could go either way. What the Southeast University result did was plant a flag on the hardest version of the problem. A single material that both makes power and keeps it, strong enough to build with and durable enough to forget about. Whether that flag turns into real buildings or stays in impressive paper comes down to who scales it out of the lab and into the concrete truck first. So the next time one of those clips slides past you, promising a magic Chinese battery brick that runs your house, you'll know what's really underneath it. It isn't really a brick, it isn't a battery, and it didn't start in China. What it actually is might be bigger than any of that. A genuinely staggering idea that the walls around you don't have to be dead weight, that the most boring material on Earth could spend the next century generating and banking power in near silence. Which raises the obvious question this video only touched: the storage half. The concrete that holds a full day of electricity in a foundation and is already stunning the engineers who test it. That energy-storing concrete is the story sitting on screen right now, so go watch it next.